Hello, and welcome to the Mathematician's podcast, the podcast where we follow the fascinating stories behind the people that count in the history of maths. I'm your host, and today we are taking a break from our philosophical and theological debates on the nature of infinity, separating the heavyweights of the age, John Philoponus and Simplicius, with an intellectual heavyweight from our own age, in another of our special sub-series episodes of The Injectives, whose function is for me to talk one-to-one with someone far more qualified than myself. Today, I'm welcoming onto the show a previous guest of the maths chat show Unnatural Numbers. She is a maths communicator and researcher at the University of Leeds. Her broad title might be set theorists, but her particular interests are is infinity. Welcome, Hope.
Hi, Ben. Thanks for having me.
So perhaps we could start with some easy yes-no questions just to get the listeners warmed up. In fact, these questions come from my school students. Am I allowed to divide by zero?
So generally, no is the answer. But if I'm answering this as a mathematician, when we have questions like this, we really want to nail down, okay, what set of numbers are we talking about? What rules are we using? So usually when we ask a question like this, we are thinking about, say, the field of real numbers. And if you look carefully about what zero means and what the rules of this kind of structure are, then no, we definitely can't. But very occasionally, there might be different instances to the kind of division by zero that we're used to, where these things are allowed. So for example, it's not something that you will hear talked about very much, but there is an algebraic structure called a wheel in which you can divide by zero. But generally, the answer is definitely not.
So it's no unless you're wearing like full PPE and you've got the qualifications to do it safely. All right, cool. So is 1 divided by 0 smaller than 2 divided by 0?
My answer to this is that neither 1 divided by 0 nor 2 divided by 0 is well defined. So it doesn't really make sense to say that one is smaller than the other. What we can talk about is limits. So what we could say is if we had 1 divided by n and we let n tend to 0, then 1 divided by n would tend to infinity. This is something that is well defined. And if we do the exact same thing, 2 divided by n, where n is tending to 0, this whole thing, 2 divided by n, that also tends to infinity. So in some sense, the same thing is happening, but we can't just divide like that.
Good. So I'm sensing that yes-no questions aren't really the field for mathematicians. I think you'll like the next one then. Is the mass of the universe finite?
Well, my answer is if the universe itself is finite, then yes. If the universe itself isn't finite, then probably, but I have no idea.
Okay, maybe you need to ask an astronomer that one, because my next question is the volume of the universe finite? And you can guess where this is going. Is the density of the universe 0?
Well, if we think about this in terms of, mass divided by volume, if we are dividing by something infinite, again, that isn't something that's particularly well defined. We can't just whack an infinity at the bottom of the fraction and work like that.
Yeah. Okay.
But,
I mean, you can see these are the kind of questions that a school student might ask, and they are
absolutely.
Perhaps maybe a little bit more silly than they are serious. So let's get back to the history and the story that we've been telling. So far, in the history of maths, we have first encountered infinity in 2 places. That of the exceedingly large and also the exceedingly small, the infinitesimal. So think Democritus with the atoms or Eudoxus with the method of exhaustion. We meet the very small again with more formality when we approach Newton and Leibniz. Happily, I will fight anyone who says that Archimedes didn't use calculus, but I understand that Newton and Leibniz were not widely accepted in their own time with the use of the infinitesimal, and it took Weierstrass and Cauchy some 200 years later to formalize the epsilon delta idea of a limit. So here's my question. Is an infinitesimal just another way of considering an infinity, but in a way that is used day to day in a classroom? Or is there something fundamentally different about considering something to be infinitely large compared to something infinitely small?
So one thing that I would pick up on immediately is infinitesimals are absolutely very important if we think about the history of how calculus was developed. But we don't really use infinitesimals in modern day calculus anymore. Um, those were phased out. When we look back at the history, our definition of real number didn't used to be as precise, so it's not a clear-cut line of when this change happened. I spoke to a friend of mine who works in this area. He thinks probably around Weierstrass is where we can kind of draw the line. But yeah, absolutely. When calculus was first being developed, we used infinitesimals. But now, if we look at these epsilon delta definitions, the point of the epsilon being used here is it's just a real number. That's all it is.
So
But
for
the point
listeners,
is,
epsilon's the really small one.
yeah, exactly.
Yeah.
So an infinitesimal, we used to use one infinitesimal that is smaller than everything else. But now the point of an epsilon is we use these epsilon delta definitions, right? And we can kind of think of these as a conversation between two people. So if I say, something is, within 5 plus epsilon, so it's really, really close to 5, the point is, for any epsilon, so for any real number you say, I can find some delta that's smaller than it. So it's essentially like you're someone's trying to prove you wrong, and you're going, no, no, I'm always going to be really close to it. So say you're going, no, I don't believe you. You're not closer to 5. Can you find me, some delta that's closer to 5 than 5.5? And I'd say, yeah, I'm within 5.25. And you could say, oh, but are you within 5.125? And I could go, yeah, I'm within 5.116. But each time this epsilon is just some real number, and I'm finding you some other real number that's closer. So we don't really use infinitesimals anymore. So that's my first well actually to clarify.
Okay, I'm going to give you only 10 well actuallys during this interview, so use them wisely. And for listeners, there are about 10 questions coming up. Yes. Okay, well that's interesting then. My jaw actually did drop when you said we don't use infinitesimals anymore, because despite having done a maths degree, it was so long ago that I forgot how it all works. So let's stick to the infinitely big then, shall we? So to remind listeners, last week we began with what will turn into an academic war between Simplicius and Philoponus over the validity of the Aristotelian view of infinity. The basic premise that both teams agree on is the dichotomy of a potential infinity and an actual infinity. So I could carry on counting indefinitely by adding 1 every second, but I would never reach the end. So that is the potential. But maybe I could have accumulated infinite number of seconds already to have actual infinity. And this is where John Philoponus and Simplicius start to have a fight. So Hope, is this dichotomy of actual and potential infinity, does that still have any relevance in modern maths, or do we no longer make that kind of distinction?
To a degree, it is, yeah. It's not something that causes problems, but the way that we use infinity in different sort of branches of mathematics are kind of similar to these two different things. So if we think of the maths that we would do in what we call analysis in, say, an undergraduate maths degree, analysis is essentially the maths behind calculus, so behind differentiation, integration, and also, how do sequences work, how do series work, that sort of thing. And you heard me previously talk about tending to something. So we might have a sequence that tends to infinity. So
this is where we use limits, is that right?
Yeah, exactly. So here, that's kind of like a potential infinity. We are getting, so say just the sequence 1, 2, 3, 4. We're getting closer and closer. The sequence tends to infinity, but we don't actually reach it. Whereas, especially in set theory, which is the branch of mathematics that I research, we talk about actual infinity all the time. Infinite sets are our bread and butter. And this isn't something that is in any way sort of problematic or controversial in maths anymore.
Infinite sets as bread and butter definitely sounds like a hotel buffet I can get on board with. Okay, so let's talk about Philoponus. So one argument that he uses to mock the concept of an actual infinity, this will be your bread and butter, is with regards to time. So the idea that you could add one day and maybe have an infinity plus one. So as in if we've already had infinite time since the non-beginning of the universe, we're at infinity, tomorrow is also infinity. Is it nonsensical to consider an infinity that could be increased?
So there are kind of two senses in which we could think of increasing an infinity. So one is, can we add more objects to an infinite set? This is, very similar to this, okay, can we add an extra day argument? And another way of thinking about this question is, can we have an infinite set with some sort of larger size? And the answer to both is yes. So some terminology that I'll introduce at this point is when set theorists talk about numbers, we tend to speak about ordinals and cardinals. So ordinals we can think of basically as generalizing the idea of enumerating something. So, 1, 2, 3 being the first thing, the second thing, the third thing. And cardinals we can think of being used to measure the size of something. So how many things are in a particular set. So when set theorists talk about how big a set is, we will say, what is its cardinality? That's what we mean. So can we add more objects to an infinite set? So if we think about the natural numbers, so this is the kind of fancy maths name for just the counting numbers, 0, 1, 2, 3, or depending on your persuasion, 1, 2, 3, etc. If we think about this in terms of being an ordinal, set theorists will use the Greek letter omega, which looks a little bit like a W, essentially to describe this same set. This is our kind of first infinite set. And we can absolutely define omega plus 1. We've added something else onto this set. So can we add more objects? Yes, absolutely. But the important thing to note here is that omega and omega plus 1 have the same cardinality. They have the same size. If this is a concept that you've not come across before, this might sound a little strange. But having, infinite sets with new objects in that are the same size isn't something that is, very new or controversial somehow. So a nice example here is the natural numbers and the integers. So the natural numbers, 0, 1, 2, etc. The integers also including -1, -2, -3. So there's a bunch kind of extra stuff in the set of integers, right? There's all these negative numbers. But what we can do if we're really clever is if we compare the size of these two sets, what we want to do is create a one-to-one mapping between them. It's what mathematicians would call a bijection. So it's essentially, the way I like to imagine it is, think of, could you line up all of the objects in each of these sets and have them each hold hands with exactly one thing from the other set? And we can do this with the natural numbers and the integers. So imagine that we match 0 with 0, and we match 1 with 1, 2 with -1, 3 with 2, 4 with -2, etc. If we keep on going like that, we have an exact matching between these two sets. They have to be the same size. They have the same cardinality. So to summarize what I've just talked about, we can add extra stuff to an infinite set and it still be the same size. That's all nice and well-defined. We've checked it, it works. But something I also mentioned earlier is we can have infinite sets of different sizes as well.
Okay, so I think that leads me nicely into the next question then. So if we if we cannot change the quantity of things in an infinite set to have a different size, but we still added more things into it, how can we get from an infinity of one size into an infinity of a different size? And what does it really mean for one infinity to be bigger than another?
So, okay, usually where this comes from is using one of our axioms of set theory, so our kind of baseline assumptions, the rules by which we do maths, which is called taking the power set of a particular set. So for finite things, this is pretty straightforward. So it's essentially you're creating a set with every subset in it. So say it was the set of 1, 2, and 3. In a power set, we would want, okay, the set containing 1, the set containing 1 and 2, the set containing 2 and 3, the set containing 1, 2, and 3, etc. If we then start applying power sets to infinite sets, this is where things can get interesting and we can start kind of increasing the sizes of infinity. So maybe the nice thing here is to look at this from a historical context. So the first mathematician to first kind of discover that there are more than one sizes of infinity is Cantor. So we've spoken about the real numbers and the integers. We also have a set of numbers called the rationals, which are essentially everything that we can express as fractions. But another very important set of numbers are the real numbers. So here we're going to add in things that are what we call transcendental. So something like pi. This is something that we can't express as a fraction, and we also can't express as the solution to some polynomial with integer coefficients. So we can't solve an equation and pull pi out if the coefficients are rational either. So this is
so if I understand you correctly, does that also mean we cannot represent it using a string of natural numbers? Because if we could create a polynomial that had only integer values as the coefficient, and this number was the solution of that polynomial, we could just represent it by those natural numbers. So are the transcendental ones, all the ones that are sort of outside of this paradigm of things that we could write down?
So a transcendental, I mean, we can write pi as a decimal, say, that's absolutely fine, but we can't write it as a fraction that has, an integer on the top or the bottom, and we also can't write it as the solution to a polynomial that has integers as the coefficients. Yeah.
Okay.
So yeah, there's plenty more of these than just pi. Pi is probably the best known example. E, if you've heard of that, is also one of these numbers. And yeah, the real numbers are a big deal to mathematicians. They are one of the kind of sets of numbers that we spend the most time thinking about and studying. So what Cantor did, which really kind of revolutionized mathematics in some sense and really brought the field of set theory into being, was proving that the cardinality, the size of the set of real numbers, is bigger than the size of the natural numbers, the counting numbers. What he did, this sort of famous proof that you might have heard, is a diagonalization argument. Mathematicians love to use what we call proof by contradiction, which is assume that something does work and then prove that we get a contradiction, prove that it can't have worked after all. So we say, okay, assume that the set of real numbers is countable. It's the same cardinality as the natural numbers. We can just list them all off and count them in some sense. It would take us infinitely long, but we could count them. If we write all of the decimal numbers out in a big table and we go, okay, let's change the first digit of the first one, the second digit of the second one, the third digit of the third one, etc. That is a real number that has to be different in at least one place to every other real number on that list. So we couldn't have listed every single real number. You've just proven that there isn't one on the list. The set of real numbers can't be countable.
Hang on, whoa. So just to clarify, you're saying that we've got two different types of number. So one of them is just the natural numbers, and one of them is all of the numbers, which includes every decimal and every algebraic and every transcendental number. And you're saying that it's impossible to count them all, but you can count all of the natural numbers. So the natural numbers are infinitely big and you can count them, and the real numbers are infinitely big and you can't count them?
Yes, that's exactly what I'm saying.
Goodness. Could you at least start counting the first maybe 10?
Sure.
What would you say is the first real number?
Well, this is an interesting question in a different direction, which is
goodness.
somewhat linked to the axiom of choice, which is
almost
a big part
led you into a trap
of research. So yeah, the axiom of choice is another of these kind of baseline rules of set theory. They are the foundation that we build the rest of mathematics from. Some of them are, super intuitive. So something like pairing. So if we have some set A and we have some set B, we can create a set of A and B. Super easy, right? The axiom of choice is a little bit more esoteric. Things aren't very intuitive when it holds. Things aren't very intuitive also when it doesn't hold. As standard, mathematicians assume it, but there are some people, including myself, who study what happens when we don't assume the axiom of choice. So let me maybe quickly define to you what I actually mean by the axiom of choice. So essentially, the idea here is if we have some collection of sets, we're assuming they're non-empty, we can have something that we call a choice function, which selects exactly one element from each set. In the finite case, we can always just write this function by hand. But in infinite cases, we have to make a rule that says that we are allowed to do this because we can't by hand write down this function. We just assume that this function exists. So the axiom of choice is also equivalent to two very sort of key principles in pure mathematics. One is called Zorn's lemma. This is the statement that every vector space has a basis. Again, in the finite case, we can just prove the vector spaces have bases by hand. In the infinite case, things get a little bit more complicated and we have to employ this axiom. The other is what we call the well-ordering principle. And that's essentially looking at, okay, if we take any subset of something, it has to have a first element. So if we just look at the natural numbers, it's very easy to have a well-ordering on that. 1 is our first element. However, if we were going to look at the set of real numbers strictly between 0 and 1, so not including 0, what's the first element in that set? Okay, it's not. If we just look at the kind of normal less than relation, okay, well, it's not 0.1 because I combine something smaller than that. It's not 0.01. I combine something smaller than that.
The epsilon.
Sure. But in fact, this kind of less than relation isn't a well order on the real numbers. By our usual interpretation of less than, there are plenty of kind of subsets of the real numbers that don't have a smallest relation. I think one of the things that can make the well ordering principle quite unintuitive is people will often describe this relation as smallest. However, what we're saying is there exists some sort of relation, some sort of ordering where we can always do this on the reals or any set that we can think of.
So I think if I summarize my understanding of what you've said, you're saying that all of the real numbers are not countable, but you can definitely count the first 10 as long as we define the word first in a creative way, being the first ones you might think of when you look at the real numbers. So you can't necessarily count them in a size order at all, but you could count them in just a random order. I could list you 10 real numbers.
Sure, sure. And being able to order any 10 numbers, I could just write you an ordering by hand. The kind of difficulty here comes when we have infinite subsets.
Yeah.
But yeah, the thing that makes the axiom of choice somewhat unintuitive is we're saying there exists an ordering with this property, but we're not saying what that ordering is. And in fact, we can't ever really say what the well ordering on the reals is.
Okay.
That's what makes it kind of not very definable somehow.
Okay, it's interesting that you've used the word definable there, because I'm going to link that back to some history from the show. So Cantor has opened the box of the idea that infinite sets can be an actual, real, tangible, describable thing, and the key word is describable. Listeners might recall that I made the claim a while ago that Aristotle invented set theory. I don't know if you have an opinion on that, but the idea of a set being a collection of describable things, that's pretty intuitive. So this ability then to be able to describe an actual infinity and have that listed and labelled as a set, does that cause any issues with the way that we've defined set theory up to Cantor?
So maybe slightly later than Cantor, but not very far after him, we get what we call retroactively naive set theory. So our first attempt of picking these axioms, these rules, as a foundation to build the rest of mathematics from. So you've heard me talk about ZFC. I don't think I actually said what that stood for. So that is Zermelo, Frankel. These are the last names of two mathematicians. And C stands for the axiom of choice. So ZFC was kind of our attempt to after naive set theory. And I think what you might be
when you say naive set theory, can we interpret that as just incorrect set theory or cute set theory? Like, is it now sort of fundamentally null, the naive set theory?
There are several of the axioms that were defined in naive set theory that we keep because they don't cause problems, but some of the axioms we had to kind of get rid of and bring in a new, shinier version that doesn't break things.
Okay.
And yeah, I think what you might be leading me towards the kind of the thing that breaks here somewhat is what we call Russell's paradox. So something that we can kind of, naively define if we just kind of think of defining a set using any property that we like is, okay, think of the set of all sets that don't contain themselves. Does that set contain itself? And this is a paradox, right?
Yeah, that's the barber's paradox of the barber that shaves everyone who doesn't shave their own heads.
Yeah, this is the exact same idea going on. And essentially, we weren't careful enough about how we set up our rules for how we make these different sets. And this led to some contradictions. So what we ended up doing is tweaking one of our rules slightly. So going from the axiom of comprehension to what we call restricted comprehension. This allows us to avoid constructing any sets that would have contradictions like this.
When you say the axiom of comprehension, is this the one that I mentioned of it has to be describable?
So the issue here is before this was restricted comprehension and was just comprehension, we would essentially basically say for any property, there exists a set of all of the things with that property. But that is essentially, that's kind of too naive. Just saying any property, that's the thing that causes us problems. So, for example, the property here could be, the set of all sets that don't contain themselves. That's where we got this paradox from. We would kind of write this properly in mathematical notation, but it's exactly what I'm describing with words. So here, what we changed it to is, okay, given a set and a property, there is a subset of our original set with all of the things that satisfy this property. And if we phrase the axiom like this, then we can't run into these paradoxes anymore.
Okay, all right. So if you're dancing around the ZFC axioms, and I think they mean a lot more to you than to me, because I didn't know about them until starting researching for this interview. One thing I love about maths is how it can so often be categorized as obvious intuition, just written down in words, or magic spells that mean little to any mortal. And everything seems to fall into these two categories of, well, yeah, it's obvious, or what on earth does that mean? So can we play a quick game of I say an axiom and you say what it means, and then I'm going to do a thumbs up or thumbs down for if it makes obvious sense or if it is magic spells. Does that sound good?
Yeah, absolutely.
Okay, cool. So for listeners, these are all of the ZFC axioms. I get the difficult job of reading out the words on my screen. Hope gets the easy job of describing them simply from memory in a way that a layperson might understand. 1. The axiom of extensionality.
So this is maybe the most obviously axiom that there is. But this is essentially the idea is two sets are equal if they have the same elements. And if two sets have the same elements, they are equal. It's an if and only if statement.
So didn't even need writing down. That one's just obvious, definitely. Okay, the axiom of the empty set.
So let me use another actually. This will sometimes be written down in your list of axioms, and the existence of an empty set is very, very important in set theory. However, we can actually derive this from the other axioms. And our job in set theory is kind of assume as little as possible, prove as much as we can. So technically, we don't need to assume this. We can derive the fact that there exists an empty set from the other axioms.
Good. So not only is it so obvious it doesn't need writing down, some people don't write it down and instead use magic spells to prove it, I think is what I'm getting from that. Number 3, the axiom of pairing.
So this is something that I mentioned earlier. So if we have sets A and B, there is a set that contains A and B. And another thing to note is if you are clever with how you use this, we also use the axiom of pairing to define an ordered pair. So usually if we write things down as a set, we write them down in curly brackets, and the order that we write them on kind of has no bearing on any order between them. But yeah, essentially, if we use a nice trick, we can write down, the set containing X and Y, and in the order X and Y. And this is a very useful thing to be able to do as a mathematician. We use ordered sets all the time.
Okay, so I'm feeling that one sounds obvious that there exists a pairing. Yeah, okay. Try the next one then. The axiom of union.
So if you're familiar with the word union from looking at like Venn diagrams, say, it's exactly the same thing that's going on here. So if you have a set of sets, then we can find a set that contains all of the elements that were in all of those different sets. It's essentially combining sets together exactly in the way that you would in a Venn diagram.
Yeah, that one's obvious. I think that one didn't need writing down. Number 5, the axiom of the power set.
So again, this is something that is pretty obvious in a finite case, but in the infinite case has really important consequences. So it's this idea that I was describing before is if you have a set, you can create a new set, which is all of the subsets of the original set.
So that's that. We like this one then because this is feels obvious up to a point and then very rapidly turns into magic spells when you do infinite sets. Okay, we like that. Axiom 6. This is the axiom schema of replacement.
So firstly, let me talk about what this word schema means. So for all the axioms that we've looked at so far, we're basically saying there is one rule that we can do this. When we have an axiom schema, we're essentially saying there are infinitely many rules saying that we can do this with all of the different possibilities. So the other thing that's kind of baked into our foundation when we're doing set theory is none of these axioms ZFC, but what we call first order logic. So essentially, the maths behind being able to things like and or implies, that sort of thing. So we also have these kind of logical rules going on.
For listeners, we met that with Chrysippus at first, and then we saw it again with Boethius a few weeks ago.
Okay, amazing. So yeah, the idea here is we have some set and we have some formula in our first order logic, and we essentially can create a new set if we look at the kind of images under that formula, the new things that formula creates, we can make a set from these things. And the reason that this is an axiom schema is we have to be able to say that we can do this for every formula in logic. That's why there are kind of secretly infinitely many rules happening here.
Gosh, that one's definitely not intuitive, but it doesn't quite feel like magic spells territory. That's more like a recipe for puff pastry. It's out there, but I could just about get on board with it. Okay, what about the axiom of infinity?
Yeah, essentially we are just saying that there exists an infinite set. We wouldn't be able
infinite
to.
Set?
So we say an because from the existence of one, we can kind of derive the existence of more than one. So you'll sometimes see this in words written as there exists an infinite set or there exists at least one infinite set. If you have done a set theory course, you will sometimes see this written a bit more technically as there exists an inductive set. And kind of baked into that is saying, okay, there's definitely one, and if we're careful, we can show that there's more than that.
So it's like when I go to the pub and I say, oh, I'll just have one. But that implies there's going to be more. Okay, good. So what about the axiom of regularity?
So yeah, this is also called foundation, and essentially the idea here is that things are somehow well-founded. So we don't have kind of infinitely descending chains somehow. So we can have sets within sets within sets finitely many times, infinitely many times. That's can be a little bit of a problem somehow.
Isn't that when you start doing a power set of an infinite set, you'd get sets within sets within sets?
Sure, but the if you keep kind of doing a descending chain, the descending chain has to end somewhere. Okay. That's if we don't have that, that's what can give us some issues. Okay. And yeah, the other thing that foundation proves really rigorously is that no set is an element of itself. That's another thing that if we don't assume, we can run into problems with defining things kind of naively.
Okay, great. So we've got another schema coming up. This is the axiom schema of specification.
Yeah, so again, this is another schema. So there's kind of secretly infinitely many rules going on. And this is what I was talking about before. A few of these have different names. I was calling this restricted comprehension before.
Okay.
So essentially talking about, okay, we want to define some property and think of the subsets of some set which have exactly that property. That's now a new set that we're able to work with.
Okay, I love that description of there's secretly infinitely many rules going on. It's like the ZFC axiom say, don't worry guys, I've just got 10 axioms, just 10 axioms some of them are infinitely long, but just 10 axioms that you need to learn. But that brings us now onto the last one, the 10th one, or indeed whichever one you want to put it as, the axiom of choice.
Yeah, so again, I spoke about this briefly earlier. So the simplest way to phrase this is maybe for every set, there exists a choice function. So we have, often we think about this as some family of sets, and I can say that there exists some function that picks exactly one thing from every set in our family.
Yes, that one feels very intuitive, kind of obvious that you can always just pick something, and I'm sure no problems are going to arise depending on whether you include that one or not. So now that we've got the ZFC axioms and we have thrown naive set theory in the dustbin of history and infinities are well understood, the numbers of them, the infinite numbers of them and the sizes and all of that, we're all happy. Does that mean this is the end of history? Certainly with regards to set theory and infinity. Do all mathematicians rally to the banner of ZFC as the solution to this 2,000-year-old paradox on infinity? Or are there any competing frameworks that people might want to research for their PhDs?
So using ZFC as your foundation is kind of the unspoken standard in modern mathematics. If you do an undergraduate maths degree, with a lot of things that you do, if you keep going, but why, no, but why, no, but why, secretly you're assuming ZFC at the bottom of everything. But
I can tell you it's such a big secret that no one told me I was doing that when I did my maths degree. It's a well-kept secret.
But yeah, the headline here is we are absolutely not done. So there are a couple of things that I want to talk about here. The first is independence and incompleteness, and the second is large cardinals. So when mathematicians were first, sort of creating the axioms of ZFC, this was kind of done in the pursuit of a theory of everything, almost, in mathematics, similar to what you'll sometimes hear physicists wanting to do. We want to find a set of axioms from which we can prove everything in mathematics. If you have heard of Hilbert's set of problems, I think was set in the year 1900, this kind of find a theory of everything was one of these problems. And one of the things that is maybe one of the most important ideas in modern set theory is this idea of independence. So there are some statements that we can phrase using ZFC, but we can't prove them to be true, and we can't prove them to be false. They are independent. So essentially, this was proved by a mathematician called Gödel in his so-called incompleteness theorems. And what this showed is we can never have a theory of everything in mathematics. What we can do is assume new extra axioms outside of ZFC, and sometimes mathematicians do, to let us prove something that we couldn't prove before. But now there will be new independent statements. There are always going to be things that we can't prove. And to me, this is amazing. I thought this was so cool when I first found out about it. And that was, to me, one of the big motivators for me working in set theory. And something that, we were speaking before about the size of the real numbers. Cantor showed, the size of the real numbers is larger than this countable set. Some notation that Cantor introduced was the Aleph hierarchy. So we say that a countable set has a size Aleph 0. The next highest size of infinity is size Aleph 1. The next highest Aleph 2, etc. And so we might say, the size of the real numbers are bigger. So do we assume they have size Aleph 1? The size of the set of real numbers, the size of the continuum, people phrase it as, is independent of ZFC. The baseline axioms that we assume in every maths degree, with those, you cannot prove what the size of the real numbers is. I think that's wild. I think that's so cool.
That is mad, because real numbers are just so fundamental.
Yeah.
There's nothing weird going on with real numbers. Okay, all right. Whew. That is interesting. So you mentioned large cardinals. What are they?
Yeah, so this is primarily what I research. So a large cardinal essentially is an extra strong axiom of infinity. So we're saying not just there exists an infinite set, but we're saying there exists these cool new, even bigger infinite sets with extra structure. And from those, we can prove new statements in mathematics. And basically, anything that is independent that we couldn't prove before, if mathematicians have found a way to prove it, usually this is from assuming the existence of a large cardinal. And we say these have stronger consistency strength from ZFC. They can prove the consistency of ZFC. So what I mean by this is the other thing that Gödel showed with his incompleteness theorems is any set of axioms essentially that's strong enough to do arithmetic in, which for our foundation of maths, we want to be able to do arithmetic, right? If it's that strong, it can't prove its own consistency. So the axioms of ZFC could be inconsistent. We don't know. Probably not. But we can't ever prove that they're not inconsistent.
Gosh, so this is going to link in really, really well when we do more history, decades from now, and we get to Cartesian philosophy and his method of rigorous skeptical doubt, and we start thinking, well, what can we really know about anything? And Descartes says, well, we start with nothing and then we build up, and then from that we can know things, and then he basically kick-started most of modern physics. And then you're coming onto the scene and saying, nah, even then, can't prove anything. We have to doubt it all. And yet you still manage to find people to pay you to do more research in this area, which is a bold move. We don't know anything, but give me another year and I'll see if I can not know a bit more. That's really nice. I like that. Okay, so on a bit of a broad summary of the historical journey of infinity, we have Aristotle starting things off by saying maybe infinity exists, but only in a sort of loose potential way. Nothing can ever really actually happen. Then fast forward a few thousand years, and we have Cantor saying actually infinities are real, and we not only are they real, there's more than one of them, and we can measure their sizes. And then you're coming along and now saying that not only do infinities exist and there are different sizes, but also we think that there's some even more infinities that no one's ever looked at yet. And I'm going to try and work out what they are. What a journey. So on a more personal note, what is it about set theory in general, or infinity in particular, that really motivates you? What gets you out of bed in the morning and over to your chalkboard, which I also assume is in your bedroom?
I mean, at a very fundamental level, I think part of the reason that I do this job is I really like puzzles, and I get to solve puzzles for a living. And I think in some sense, I've always been a very broadly curious person. I was always the person, with my hand up in the classroom. And I was also that person, especially as a little kid, who was going, why? No, but why? No, but why? And if you take this approach of going, no, but why, no, but why, and you apply it to mathematics, what you get is set theory. If you say no, but why once more, then you get philosophy of set theory. And this is very cool. And it's something that I am also very interested in. But yeah, I think it's this idea of really looking at the why of something. To me, that's kind of the ultimate puzzle to solve. And these things are very unintuitive, but I kind of delight in how unintuitive they are.
It's almost like you're describing the branches of mathematics as being a long road with lots of turnings off at different points, and everyone can follow the road of maths and then stop when they want to really dig in and investigate why. And for me, when I did my degree, I did most of a maths course without really doing any advanced set theory, got right through to the theoretical physics, and then I did my master's in fluid dynamics. And that's when I stopped and said, right, let's work out why these fluids act the way they do. But it sounds like you stopped at the very first gate and said, right, what does any of this mean? And you're almost describing set theory as like the most fundamental, foundational why of all of mathematics, which is pretty cool. That being said, so a lot of people might think that a mathematician goes to university and just studies all of maths, but actually it's a huge and diverse field, to the point where I did 4 years at university and never really touched the stuff that you're talking about. In order to get to where you are, presumably you had to do your master's thesis in set theory or PhD in set theory specifically, and then infinity in particular. What encouragement might you give then to someone who is just starting their maths course as a first year undergrad to say, come on board the set theory train and put your specialism in set theory? How might you convince them that it's cool?
I think one of the things to think about if set theory is really something that's going to make your heart sing is, are you someone who really likes the big picture, broad strokes, or are you someone who really wants to look at details and dig into why something works? And if you're the latter, something like set theory might be for you. I would say set theory isn't always the most broadly taught thing in a great level of detail. For myself, I really wasn't formally taught much set theory before my PhD. I took a course in logic from the philosophy department, actually, and I did, in a pretty self-taught way, write my master's thesis on set theory. But yeah, especially in the UK, if this is something for you, it is something that you might have to follow your nose on a little bit. But there are a lot of resources out there.
All right, cool. Well, hopefully that will resonate with someone listening to this. So thank you, Hope. This has been an absolute pleasure, or so it says in my script, which I wrote before discovering whether or not it would be an absolute pleasure. But on this occasion, I can confidently say delete as appropriate. You have certainly answered all of my questions and given me a lot to think about as the basis of the next time I badger you with questions over WhatsApp. So before we say goodbye, can I give you an opportunity to talk about anything you'd like to? What projects are you working on? Where can people find out more about you? Or how would you like to direct the audience today?
So the project that I'd most like to share is my work on YouTube. So you can find me on @HopeDuncanMaths on YouTube. I have a series at the moment called Fake It Till You Make It, where I look at the work of other maths creators on YouTube that I really like, and I explain a little bit of maths in their style, and essentially it's a little bit meta, but talk about how I found communicating in that way. It's my journey of kind of improving my own ability to communicate maths by looking at what some of the people that I grew up watching do. So yeah, Hope Duncan Maths on YouTube, and you can also find me on Blue Sky, where my handle is @hopeiona.bluesky.social.
Thank you, Hope, once again. So that's it for today's episode. You can find me on Blue Sky at mathematicians-pod if you want to ask me any questions, or Hope, who is at Hope Duncan Maths on YouTube and Hope Iona on Blue Sky. Next week, we will continue the rap battle and give Simplicius a right to reply to Philoponus next week on the Mathematicians podcast. Until then, goodbye.
Goodbye.
The music today is Dance Macabre Finale by Kevin MacLeod. You can find more information in the show notes.